All right, it's recording. All right. Today we're going to do the types of chemical bonds, and also the big chunk of this chapter is naming chemical compounds. We're going to be naming our covalents and our ionics, and there's rules that go along with each naming scheme. So it is a lot, but it really, if you follow along, it shouldn't be too hard, and it creates a foundation for everything that we're going to do in the class. Every time we talk about chemical reactions, which will be later on, we'll have reactants and products. These reactants and products will be compounds. These compounds will have names. So it's very important that you be accustomed to naming these compounds very easily without thinking about it much. So we'll do a lot of practice, and hopefully we'll get it down by the end of class. If not, you have the homework assignments to guide you. Okay. So chemical bonds. There are two major types that we're going to cover. So you have our ionic bonds and our covalent bonds. Now, technically, they're all electrostatic interactions, right? That's the thing in biology and in chemistry, that everything is governed. All these chemical interactions are guided by electrostatics. But ionic bonds are the fundamental electrostatic and one of the strongest electrostatic interactions, because they directly involve oppositely charged molecules, a positive and a minus, and a positive and negative, just like we talked about last class, where we did mention cations and anions, but and we did talk about it. So it was part of the lecture just to get you into this. So the ionic bond is directly related to having a positive cation and a negative anion. So a positively charged particle and a negatively charged particle. These particles, these either atoms or molecules, they can be either atoms or molecules. You could have a positively charged just singular atom, which is most of the case. You'll have sodium, potassium, strontium, things like that are positively charged. Sometimes you might have what we call polyatomic ion. So what that means is an ion that has a charge that contains more than one atom in its molecule. So for a cation, you would have ammonium, NH4+. That is a polyatomic cation. For anions, same thing. You can have singular atoms, such as chlorine, which is a -1 charge. And we did talk about the charges in the periodic table last class, but we will go over them again. And you could also have most of the polyatomic ions are anions, meaning they have a negative charge, such as carbonate, phosphate, nitrate, sulfate, and all of those ones that maybe we've heard of some of those without even taking chemistry, but they have negatively charged, they're negatively charged entities in a whole. So we'll talk about that as we get into the naming. Then we have covalent bonds. So covalent bonds, it is technically governed by electrostatic interactions, but in general chemistry, we refer to them as they're sharing the valence electrons between their atoms. So for example, this right here is peroxide, hydrogen peroxide, where they're making covalent bonds between the hydrogen, the oxygen, between both the oxygens, and over here between this oxygen and the hydrogen. And that is governed by the covalent bonds, meaning they're sharing the valence electrons between each oxygen, the hydrogen, the oxygen, and etc. There's a lot of shared bonds in there. So just know that or shared electrons in there. So just know that for now. Okay, so here's exactly how it happens. So I mentioned last class about how the common misconception that sodium is just innately positive and chlorine is innately negative, and when they come together, they make a bond. That's not true. And that's not true for any ionic bond. And this GIF shows it perfectly, that initially they're neutral. You see how there wasn't any charge in the beginning of the GIF? But since they get close to each other and based on their need or lack of need of valence electrons, they induce a transfer. So what that means is chlorine is initially neutrally charged and has 7 valence electrons because it's in group 7A. And we did talk about that last class, I believe, that the main group elements, like if you see my video, I'm gonna point right here. If you see like my background, this is good, I could use this. So right here, these elements are the main group elements, the ones that are up here and also the ones that are on the other side of my head right there. Those are main group elements, meaning you have 1A, 2A, you skip over the middle section, 3A, 4A, 5A, 6A, 7A, 8A. And that A refers to the number of valence electrons. So for chlorine, chlorine's located right here in 7A. So that means it has 7 valence electrons. And in order to obtain the noble gas configuration, or the noble gas number of valence electrons, which is their goal, it wants to have 8 total. In order to do that, it needs 1 more. That 1 more, sodium happens to come around. Sodium is right in group 1A right here. And sodium wants to do the opposite. It wants to get a noble gas configuration, but there's 2 ways for it to do that. One is by gaining 7 electrons, which is highly unlikely and requires a lot of energy, or by very simply losing 1 electron, the only electron it has, the only valence electron it has. So it will be right here, and then it will lose its valence electron, and then its configuration will look like over here. I think it's neon. So once that happens, it induces a charge, because now the electron number is different for each of the atoms, and it's not the neutral number. So the neutral number of electrons for sodium, it has 11 protons, it's atomic number 11. For that, it would be 11 electrons, which would make it neutral, right? Because if the protons equal the electrons, it is neutral. Then, once 1 electron is removed, like the GIF shows, and transferred to the chlorine, that induces a positive charge on the sodium, and also induces a negative charge on the chlorine, bringing them together. So that is how ionic bonds form. Okay, next one. Oh, then is there a GIF there? No, I guess not. Wait. Okay, whatever. But in covalent bonds, it's a little bit different. So here you have an oxygen on the right side and a hydrogen right here. So for the oxygen, which is here, it has 6 valence electrons. Now, hydrogen only has 1. When they want to make a bond, so based on covalent rules, which we didn't really cover Lewis structure yet, but when we do, we'll go into this in more detail. But hydrogen wants 2 electrons total. It's so small, they can only fit 2 electrons. If that's the case, it needs 1 more electron. Oxygen is a non-metal, just like hydrogen. So also it's also important to keep in mind non-metals and metals, right? Because ionic bonds, it's always between a metal and a non-metal, or non-metals. Covalent bonds is between non-metal and non-metal. So you'll see that the same rules apply with the need for a complete valence electron shell, meaning for most elements, 8. So oxygen has 6 valence electrons. It's right here. If you look at my video, I'm pointing to oxygen as in group 6A. So it has 6 valence electrons. It wants 2 more. 1 hydrogen comes along. I'm going to draw this on I'll use my pen. I'm going to draw this on a different slide. I'm sorry if I'm going too slow for some of you who took the course already, but some of you did not. Where's my pen? Okay. So hydrogen, where are we at? There it is. Okay, so hydrogen. Oh, that's not. Why is it doing that? Okay, fine. So, this is like, it's not writing where I want it to write. All right, cool. So, no, it's not writing where I want it to write. Okay, whatever. We get the point. Well, I think we get the point. That if we have hydrogen, it wants 2 valence electrons total, and it needs to share 1 with oxygen. If it shares 1 with oxygen, oxygen will now have 7. Hydrogen will be happy. Another hydrogen comes along, does the exact same bonding interaction with oxygen. Oxygen now has 7. It's like, oh, give me, I need 1 more. It will take 1 from hydrogen and it will give 1. So it will share an electron with hydrogen. Hydrogen will be happy and oxygen will be happy. So I do need to draw. This is a pain in the ass. I gotta see what's going on. All right, so hold on. I'm sorry for the technical difficulties. I've been doing good so far, but where are we at? It keeps writing. My cursor's on the left side. It keeps writing in the middle. Okay, I guess we'll deal with it. So hydrogen. No, I can't do that. It's just not going to work. It'll create more problems. Okay, I'm sorry about that. But let's just keep going. Is there any questions about how those two bonds form? That's really integral to learning. No? Okay, cool. All right, moving on. So here is a reiteration. Oh, there's a chat. Let's see. Nope, okay, everybody's good. All right, good. So they'll only put in questions in the chat if you have a question. If you don't have a question, just don't say anything, because then I need to open up. I don't see the chat window on here. I gotta click it again. So it's all right. All right. So here is a periodic table showing the charges that. This is a very comprehensive table I got. It shows the charges of all the monocharged, meaning all the elements in the periodic table that have only a singular charge and they don't really change. So everything that's blued out has multiple charges. So all the transition metals, the post-transition metals, some of the metalloids, you know, they could have weird features, weird properties. But the important things to know, main important things are 1A is +1, 2A is +2, 3A, aluminum and even gallium, but aluminum is the main one, but aluminum and gallium, if you'd like to remember those, have +3. -1 is the halogens. So you have fluorine, chlorine, all the halogens right here, 7A. -2 is 6A, -3 is 7A, or sorry, -3 is 5A. And I'll explain why that is in a second. And then you have these three nomads right here, right? You have zinc, cadmium, and silver. So, and it kind of also follows a trend. But even though silver, zinc, and cadmium are in the transition metals, they still, I guess they didn't know where to put them because they only have one charge. Silver is always +1. So you don't really say silver 1 chloride, you just say silver chloride because it's known in chemistry that it only has a one charge, a +1 charge. Zinc and cadmium, same thing. You don't say zinc 2 chloride, you say ZnCl2 or zinc chloride. And the reason why is because it's known that the only charge that zinc could have is +2. And same for cadmium. And you see the trend that from group 1A to 2A goes +1, +2, obviously. And then for silver, it's +1, zinc and cadmium +2, aluminum and gallium +3. So that's a really cool little staircase trend right here. And then it goes down from -3, -2, -1 to 0. And the reason why is because if you look at the halogens, they have 7 valence electrons. They need one more electron to get to 8. When they get that electron, it becomes negatively charged, -1. Oxygen, sulfur, selenium, but really oxygen, sulfur, the main one. Selenium, I've seen it have different charges before, but according to this chart, just worry about oxygen, sulfur. So for them, they have 6 valence electrons. They need 2 more to get to 8. Once they get those 2, they will have 2 extra electrons, making them -2 charged. Same thing for nitrogen and phosphorus. Nitrogen is -3 because it has 5 valence electrons. It's in 5A. If that's the case, once it gains its 3 other valence electrons from other metal atoms, it will get a -3 charge. So this charge chart is indicative of when the atoms become ions, not immediately. So if you look at a brick of magnesium, it's not going to have a charge. When it interacts with a non-metal, then it will get its ionic charge. So this is not a natural charge. This is when it becomes an ion. It has this specific charge. So it is good to know this. All right, any questions? No? Okay. All right, let's get into naming. All right, naming. So we'll start out with the simple ionic compounds. Now, if the easiest way to learn this is by example. So there's some examples right here. Now let's use an easier example. I'm gonna write down here sodium chloride. So that's our always best go-to. It's NaCl, and we know that. Why is it NaCl? Why is it sodium chloride? So sodium, Na. It's the name of the metal. Good. That's the rule, that in any ionic compound, the name of the metal comes first. Then you have chloride. If you look at the periodic table, there's no chloride on the periodic table. There's chlorine, right? So that might mean you might have to change the ending of chlorine to chloride. And that's exactly what you do. So you change the ending of our anion, our non-metal, by removing the ending, removing the last syllable, and adding an IDE at the end. So sulfur becomes sulfide, fluorine becomes fluoride, oxygen becomes oxide. And it's kind of weird. It's not oxide. I get that mistake a lot, but it's just oxide. Whatever sounds better is usually right. So another thing that I didn't mention, well, I didn't exclusively mention, is that this is important. So this phrase right here kind of encompasses everything I just said, that little rant about ionic bonds. So metals lose valence, or metals transfer valence electrons to become cations, or transfer valence electrons to non-metal, metal cations. Transfer valence electrons to non-metal anions to make ionic bonds. So make I don't know why the window messed up. Okay, so metal cations transfer valence electrons to non-metal anions to make ionic bonds. That encompasses everything. That encompasses that ionic bonds are between metals and non-metals. And it means that metals transfer the electrons to non-metals. That's all you need to know before we get to naming. Okay, so we basically have the rules down. So that for simple ionic compounds, you have the cation, and then you add the IDE ending to the anion. So examples, and I'm not sure if you can see them right here. We'll get rid of this. Examples, CAS, C-A-S. Ca is calcium. You just name the metal. S is sulfur. So you change the ending to sulfide. So it'd be IDE, sulfide. Kf, potassium is K, so that stays the same. Fluorine becomes fluoride. Magnesium, magnesium oxide. MgO. So it becomes magnesium, you keep the metal. Oxygen becomes oxide. That's it. So let's do some examples. I'm going to write an example. And anybody could either write it in the chat or answer it. So what about Na2S? So that 2 is supposed to be a subscript. Wow, I think there's something wrong with the... Yeah, so anybody want to say that, what that is? Na2S?
Sodium sulfide.
Good. Sodium sulfide. Awesome. Now, maybe some of you were thinking sodium or disodium sulfide or something, right? But that is not the case. So for these ionic compounds, there's the simple ones, and really for all ionic compounds, do not use prefixes for ionic compounds. Very important rule. They don't use prefixes. And the reason why, by prefixes I mean carbon dioxide, right? Carbon dioxide, CO2. It has carbon and 2 oxygens. That's a covalent bond. Covalent naming uses prefixes, but ionics do not, never. Even if you have Na2P or Na3P2 or something, you're never going to use those prefixes. And the reason why is because mathematically this works out. Na, sodium, is positively 1 charged. There has to be 2 of them, +1 +2, to cancel out a sulfur, because sulfur is, if you look at the table, -2, -2. So it mathematically works out. Okay, next. What if you are dealing with transition metals in which you don't know the charge by looking at the periodic table? There's a rule for that as well. So you name it normally, and then you're going to add your Roman numeral, Roman numeral that's right next to the metal that denotes the charge of the metal atom. And I'll show you what that means. So or is anybody lost or anybody have any questions so far? I know I'm going a little bit fast, but I think the first rules weren't too bad. But if you have questions, also this is going to be on YouTube. So, so yeah. Anything? Okay. Anything? No? Okay. So iron 3 chloride. Let's break this down. So iron, Fe, it's the metal. Easy. The 3, we'll get to it in a minute. Chloride, Cl, we got it. Now let's look at the compound formula. Cl3. We know about Cl. We know about its charge. Its charge is -1. There happens to be 3 of them. That makes -3. So if that's -3, we know that the charge of the iron has to be +3 in order to counteract the -3 charge from the chlorine atom or the chloride ions. So that's why it's iron 3 chloride. For iron 2 chloride, it's the same thing, but instead of 3 chlorines, you have 2 chlorines. And that's it. Yeah, that's how that works. We'll get into the next example. Are there any questions on those two? No? Okay. Next one. Now you have it's a little bit trickier. You have copper, you have Cu2O. It's not copper 2 oxide, it's copper 1 oxide. The reason why is because you look at the ionic bond and you see oxygen. Oxygen, we know oxygen is -2. If oxygen is -2, that means to counteract -2, you need +2. There are 2 coppers there. There's Cu2. If you need a +2 total charge, that means your charge of each copper will be +1. So mathematically, you see that copper Cu +1, another Cu +2, paired up with the oxygen -2, it works out, and it cancels out equal and opposite. You can also have copper 2 chloride, or oxide, sorry, because if you have a copper that is positively 2 charged, and then that works out in a 1-to-1 ratio with the oxygen, that's -2 charged. So that works out mathematically as well, and you have copper 2 chloride. But the main thing to keep in mind is that the Roman numeral is the charge of each metal ion. So I would suggest writing that down. It's the charge of each metal ion, right here, but includes charge of each metal ion, not total charge of the metals. Because in this case, for Cu2O, the total charge of the metals is +2 to counteract the -2. But each metal ion, since there are 2 of those, needs to have a charge of +1 for it to work out. So is there any questions on naming with transition metals? No? Okay, cool. So here's what we're gonna do. So I always wanted to mix this up. All right, no, that's good. Yeah, I always want to mix this up. All right, so that's for ionic. I have a whole slide later on that summarizes all the rules, but so you can put in your notebook or whatever if you're listening. That's ionic. Now covalent. There's only one rule we didn't cover for ionic, which is polyatomic, which is very easy, but and we'll cover it later. So so covalent. Now covalent, they also call molecular compounds. So if you're doing some YouTube searches or you're trying to study later on and you see molecular compounds, that also means covalent. I still don't like that term, but I just use covalent. So let's use our examples that we know. We know carbon dioxide, CO2, okay? So it says it's between 2 nonmetals. We know that, right? Covalent is between 2 or more nonmetals. First element is carbon, and in the name, it's also carbon. So that means the element stays its name. Then the second element has a dioxide. Okay, so we've seen oxide before in ionic, meaning that we change the last syllable to IDE. So that should be good. That rule stays in both naming schemes. But the only difference is that we use this prefix to tell us the number of second elements. Also, we use it for first elements too, but I'll explain why. I'll explain this. So we use dioxide to say 2, and that's that. Carbon monoxide is something different. So carbon monoxide can kill you. Carbon dioxide, you need to live. So very opposite, only off by 1 oxygen. Now carbon monoxide, you use the prefix mono to tell you 1. Now, here's another one, water. So if you want to say water in different terms, you could say dihydrogen monoxide, because you say you have 2 hydrogens and then mono oxygen, 1 oxygen. Okay, so hopefully that makes sense. Now there is the little nuance rule of covalent bonds is that for the first element, maybe some of you noticed it from this line right here and also from the carbon examples, that the first element, carbon, does not have a prefix. It's not monocarbon monoxide. It's just carbon monoxide, not monocarbon dioxide. It's just carbon dioxide. And the reason why is there really is no reason. It's just a rule they made, honestly. Basically, the rule is when there is, oh, you have a question? Anybody have a question? Or no? It's okay if you don't. It's like your mic went on. It's cool. I'll just keep talking to myself then. Okay. You good? Okay. All right. So, if you only have one of the first element in covalent bonds, you do not use a prefix. So it's written right here. So prefixes are denoted to a specific number of atoms, except when there is just one of the first element. So if there's only one of the first element, no prefix. If there is more than one, you have to use a prefix. So if you have dicarbon monoxide, C2O, that's totally a thing. That's definitely real. So you would have dicarbon. But if it's just carbon monoxide, if you just write the singular element name as the first element, it tells the reader that, okay, there is just one of these. And it works out. Okay, any questions?
You always need to put the mono on the second one though, right?
Correct. So for always the second one, you're gonna put a prefix, whether it's mono, di, tri, etc. And we'll go over the prefixes. I think they should be here.
I have a question.
Yeah, what's up?
Why is hydrogen monoxide not a ionic bond if they're oppositely charged?
Ah, good question. So hydrogen is a weird element. So hydrogen, when it's paired up with another nonmetal, it's going to create a covalent bond, because that's easier for the hydrogen with 1 valence electron to share 1 valence electron with oxygen, so that hydrogen is satisfied with its 2. So hydrogen, it doesn't follow the 8 rule. It doesn't want to get to a noble gas. It just wants 2 electrons total. Once it shares 1 from oxygen, it's good. So it doesn't act like a metal in those cases, because even though it's in 1A, well, it's not a metal. It's not a metal. It's a non-metal, but it's with 1A. So you think, oh, it loses an electron and it makes positive 1, just like the chart said. That is true when it's ionized. But in covalent bonds with another non-metal, it likes to share an electron and actually to fill up its octet, or its valence shell of 2. So it depends on what it's with. When we're talking about ionizing or ionization, when we get to acids, which is pretty soon, we talk about it here, but in another chapter, that is when hydrogen will have a positive 1 charge, is when it is ionized alone in a solution. When it's with an element, it's usually with a non-metal, and it will create a covalent bond. So hopefully that answers your question.
Yeah, thanks.
Okay, cool. So yeah, hydrogen is just weird. So that's TLDR. Hydrogen's weird. Okay, we did this already. Cool. We know that you have 7A, 6A, 5A, 4A, and your charges. Now 4A, you don't really see carbide and silicide too much. That's why they weren't on the table, but that's a thing. But you don't really see them too much. It's not definite. Sometimes they could be different, especially for silicon. So whatever. So yeah, we've seen those before. Okay, so writing the formula. All right, so if you want to go the opposite way and write the name from the formula, or write the formula from the name. Let's say you have calcium nitride. This sucks because my pen, I'm sorry about this, the pen not working. I don't know why that is. But next class, I'm switching to my desktop with my all my high-end stuff. So I'm not gonna be on my laptop, it'll be a lot better.
Any chance the batteries are low?
No, so no, on the pad, it's USB into, I'll try to just reconnect it. That could work.
Give it the old Nintendo.
Yeah.
Are you writing on a tablet?
Yeah, I'm writing on so this is the thing, it's a XP pen, it's called, XP-pen. It was like 40 bucks, it's really good thing. And it has a 10-inch writing pad on it. It's not an LED screen or anything, it's just a writing pad. And it's got some buttons on it too. So let's see if that worked. All right, so it looks, maybe reconnecting it worked. Nope, it didn't. I don't know why. See, my cursor is by the F in formula on the top, and then when I write, it writes over there.
Is there a way to reorient it?
Yeah, probably. But I don't want to waste your class time doing that. I can get by with just writing in the text boxes. Okay, so for calcium nitride, so calcium is Ca2+, like right here. Nitride, which is the root nitrogen, is -3. So if you want to write the formula for calcium nitride, the first thing you do is write down the ions. So you write down Ca2+, and then you write down N3-. Then a cool little formula is you just do the crisscross rule. So what that means is, these arrows are in the wrong place. You go like that, and you go like that. So you take the number that's on the charge, and you just crisscross it. You bring it down to the opposite side. And the Ca would now have 3, and then the nitrogen will now have 2. And that's the answer. That's what the formula is. And the reason why is, so I'm not a huge fan of this rule because it does have one little nuance. So, but the rule I am a fan of, I'll explain the nuance in a second. The rule I am a fan of is just going mathematically. This line right here. To make a neutral compound with a net charge of 0, you need 3 calcium ions and 2 nitrides. That was your question? No? Okay. So you need 3 calcium ions and 2 nitride ions. So what this means is mathematically it works out, and you could just deduce based on the least common multiple of the ionic charges what the formula will be. So how do 2 and 3 balance out? Okay, if you have 3 of these and then 2 of these, the total negative charge of nitrogens will be +6 or -6, and then the total positive charge of the calcium will be +6. And then +6 and -6, that cancels out. But a short way to do it is this crisscross rule. You just take the numbers and put them on each side. The reason why I don't like that is because of, yes.
If you want a more general rule, couldn't you just say find the least common denominator? Or like not the denominator,
least common multiple. Yes.
So is the nuance when it's the same number?
Exactly, when it's more than one of the same number. So yeah. MgO, right? It's not going to be, or magnesium oxide. So, Mg, whatever, let's erase this. All right, so Mg2+ and O2-. We have a problem here because if you just blindly do the rule, put 2 on this side, 2 on the other side, you'll end up with Mg2O2, which is not correct. It's actually MgO. And that comes with just understanding understanding that Mg2O2 is not a thing and it's MgO. But if you're new to this and you're just, oh, I see a rule, I'm just going to use it every time, you'll get the wrong answer. So that's why I like to think about it mathematically, like you said, the least common multiple. So one of magnesium, one of oxygen go together. Okay, any other questions? No? Okay. Moving on. So let's practice writing formulas. So we're going to go through this together. So calcium carbide. So I'll write the ion. So calcium is 2 plus. Carbide is 4 minus. Now, if you, and there's another way where the rule doesn't work. So if you do the rule blindly, you see that, oh, it would be Ca4 C2 because you do the crisscross, but that's not true. You need to do the least common multiple. So if you, so if you do Ca2 plus, there needs to be 2 of them to cancel out with 1 carbon minus 4. So you'd have Ca2C. Yeah, Ca2C. That's it. Does that make sense?
Yeah.
Okay, good. Next one, barium nitride. So barium is 2 plus, I think. Yeah. So I get it wrong. Yeah, barium's 2 plus. I'm not completely washed up yet. All right, so barium is 2 plus. Nitride is minus 3. In this case, the crisscross rule will work because, and the least common multiple is 6 between the plus 2 and the minus 3. So if you crisscross them, you would have Ba3 and 2. And mathematically, that works out as well. Next, you have sodium, which is Na plus, phosphide, or which is phosphorus, which is minus 3. And to make these cancel out, you need 3 of the Na plus 1 to cancel out with 1 phosphorus 3 minus. So it would be Na3P, like that. And then the last one, aluminum sulfide. So aluminum, if you remember, it's one of those weird ones in the middle that has a plus 3 charge. Yeah, if you're not going to ask a question, you ask to turn off the microphone. Can you please? Okay, I can do that. I can mute people. Yeah, please make sure your microphone's turned off if you're not asking a question. How do I do that? Okay, seems like it stopped. Okay, and thank you, Marlon, for being the police, the turn your mics off police. No, it's okay. All right, I can mute people, but I'd rather just keep going. All right, so aluminum sulfide, you have aluminum is 3 plus, sulfide is 2 minus, which is sulfur. So you can see how it works. Aluminum, you would need 2 of these to make it plus 6, 3 of the sulfurs to make it minus 6, Al2S3. And then we can see the answers. Yay, we got it. Okay, cool. Is there any questions on that? No? Okay, cool. Next.
I just had a quick question.
Yeah, what's
Like,
up?
for an exam, we're obviously going to have access to a periodic table, right? We're not going to.
Oh, of course. Yeah. So it'll be on the exam.
Oh, okay, cool.
Yeah, it'll be like the first page of the exam. Okay, cool. All right. Good. So let's do these. Let's name these transition metal ones. Okay. So Ti is, let's see where Ti is. Where's the periodic table? Oh, I have a periodic table in I have a periodic table. I have one printed out on my desk all the time. So Ti is titanium, and it's atomic number 22. So atomic number 22, it's next to scandium in the periodic table. So if you want to look at my video, it's right there. So it's a transition metal. That means it's not going to, slide though. All right, there you go. So that means it's not going to have a defined charge. We don't know it as +1, +2, or +3. It can vary. So if that's the case, something's definitely wrong with my. All right, so if that's the case, it can have a varying charge. Now, in all of these ionic compounds with transition metals, a key rule is look at the compound, look at the formula, and be able to tell, all right, which one of these do I know based on the table? There will be one, at least, that you know based on the charges of the table that we went over. In this case, it's chlorine. So Cl is -1. There are 4 of them, so times 4 equals -4. There is one titanium, which has to be +4 then, right? So +4 equals titanium. And then our answer will be titanium 4 IV chloride, like that. Hopefully that makes sense. Let's do another one. So
Question.
oh yeah, what's up?
Will all these transition metals generally be a +1 charge?
No, so the transition metals have a varying charge. It could be +1, 2, 3, or 4. And in this one, titanium 4, it's actually +4. So the chlorine is -1, and there's 4 of them.
Oh, okay, okay.
Right. Okay. So in this
wait, I have
case,
one more question.
yeah, yeah.
So, like, you don't have to worry about, because I was thinking, what if the titanium, like, does the charges vary?
Yeah.
What if it was, but based on the formula, you know that it's only one titanium in there. So then
Correct. Yeah, it's not like a mixture of different titaniums. If you have TiCl4, that's one molecule. That's a bunch of you can have a bunch of them, millions of them. And in every single one of those molecules, titanium is 4+.
Okay.
You could also have TiCl, which is titanium 1 chloride. You could have TiCl2, titanium 2 chloride, etc. Okay.
But if you had Ti2Cl4, it would just be titanium 2, right?
Correct. Good.
Does
That's
that
how the math
exist?
works out. What's up?
Does that exist?
I think so. I don't see why it wouldn't.
Okay.
Okay, good. Good questions. All right, so if looking at PVBr2, we can just stare at it and see, what do we know? We know bromine. Bromine is -1. Br -1. There are 2 of them. That means you need -2. There is only one lead. That means the lead, Pb, has to equal +2. So you have lead 2 bromide. Is there a question? Okay. Plubum. Nice, Chris. Funny. Okay, so lead 2 bromide. That's how that works. All right, now let's do the last one. I think there's something wrong with my laptop, with the way my formatting is. Sorry for that. All right, so iron, we know iron. We don't know iron. We know sulfur, right? So sulfur, we know the ion of it is sulfide. And we know that sulfide is -2. Our formula tells us that there are 3 of them, which means that there's a total of -6. Now, this is the most complicated thing about transition metals. When you have more than one metal, we need to take -6. We need to take the opposite of -6, which is +6, which is going to be the metal charge. And we need to distribute it into the number of metal atoms in this molecule. So we need to distribute +6 into +3 and +3 because of 2 irons. So that +6 is distributed into +3 and +3 into the 2 irons. So the formula, or the name of it, would be iron 3 sulfide, like that. Okay, cool. So any questions on that? No? All right, so these are answers. Wow, look how smart we are. Awesome, cool. Okay, now polyatomic ions. So polyatomic ions, they are exactly what they sound like. So what that means is there are multiple atoms that go together to create ions. Basically how it works is that these entities, these bigger ions, are composed of covalent bonds that the entire molecule of the covalently bonded structure has a charge on its own. And these charges can interact with positive charges of metals, and for ammonium's case, which is the only positively charged polyatomic ion that we need to know, it will have interactions with non-metal anions. So here's a bunch of them, and you do need to know these. These are the ones you do need to know, the common ones. So Yeah. Simple ones, you have like carbonates, and there are trends to them, but you can take a look at these. And once we do the homework assignments and we keep saying the names over and over again, it'll become commonplace, especially by the end of maybe by next week or the week after, that they'll become pretty readily used. So acetate is a very common one, C2H3O2. The way I remember it is CHO232, and it's a -1 charge. Carbonate, CO3, anything with an ATE, a carbonate, chromate, not chromate, a carbonate, sulfate. They don't have nitrate on here. Nitrate's a really important one. Why isn't that on here? But I think, do I have a master list? Okay. I don't. I think there might be one later on, but, oh, nitrate's on here, right there. I see it. Okay, good. This is a good list then. Where's phosphate though? Okay, I need to make a better list. So you can see the ones with the ATE, they have whatever the element is, nite means nitrogen, with some amount of oxygens. So nitrate, NO3, carbonate, CO3, perchlorate, chlorate, these are all ClO3, ClO4, sulfate, SO4, things like that. So you can kind of see a little bit of a trend, but it's not too much of a trend, but it can help you memorize things. So we're going to be using these. Now, here are some that are a little bit weird with chlorine. So chlorine and oxygen have 4 polyatomic ions, and it kind of works in a hierarchy of oxygens, and they're all -1 charged. And the reason why, some of you are probably thinking, oh, if there are a different number of oxygens, why are they all -1 charged? And once we get to Lewis structures, that'll be more apparent, because the way they bond, that it either leaves 1 or more oxygens charged in one of them. So in every one of these cases, only 1 oxygen is going to be negatively charged. And we'll see how that works once we get to Lewis structures, but it's basically the bonding arrangement of the oxygens to the chlorine is what dictates that. Okay, so hypo. So you see hypochlorite. So in a nutshell, if you go back to here, if you have a polyatomic ion with an ITE ending, nitrite, for example, that means that it has a less number of oxygens than its ATE derivative. And you can see that a little bit here. Nitrite is NO2, nitrate is NO3. Sulfite is SO3, sulfate is SO4. And that's a trend. Phosphite is PO3, phosphate is PO4. So if it's kind of like a hierarchy. Hypochlorite is like, all right, I'll take a chlorite and I'll hypo it, meaning less. I'll take a chlorite and put 1 less oxygen. You get ClO. Regular chlorite, ClO2. All right, I'm going to upgrade my chlorite to a chlorate. Add another oxygen, SO or ClO3. Then I'm going to take per means more or greater. I will take chlorate and put perchlorate. I'll give my chlorate steroids and it'll be perchlorate. Give them another oxygen. So it's ClO4 minus. So it's kind of like a hierarchy. Yeah.
How do you determine what the base anion is?
You mean, what do you mean by that? You mean like the
is chlorite the base? Like, how do you know which one's going to be the lowest and which one's going to be the highest?
Oh, based on the name. So based on so like these are the definitions of them, just like.
Okay, wait, I have a better question. Like, I get what you're explaining here, but how are we going to see this in a test question? I mean, like.
Okay, that's a good question. All right, so just like the other polyatomic ions. So let's say I give you, NaClO3, name that, right? So naming that, you'd be like, okay, it's sodium, and then ClO3. Which one is that again? Oh, it's chlorate. Okay, sodium chlorate. Done.
Right.
So stuff like that.
So we have to memorize these.
Yes. That's why I'm going over how to memorize them, and like.
Okay.
Yeah, I'm going over like yeah, I'm going over how to memorize them, these little trends and things, little patterns. So, yeah. And I know, I get it. Like, it's an online class, so you have to, like, quote unquote memorize them, but you should have them known, especially if you're taking Chem 2 next semester in the fall. These need to be, like, you need to know these like the back of your hand, but you will when you practice them. A lot of people make flashcards and things like that. Okay, so let's do some examples. All right, so aluminum ion with a sulfate ion. So aluminum, so Al 3 plus. A sulfate ion is SO4 2 minus. Or SO4, I'll do that. SO4, which is a 2 minus. Now, if you put these together, the same rules apply. So it would be, we didn't go over the naming yet. The naming is really easy. So in essence, the naming, I think it comes in later slides. You just put the name of the sulfur. You just put the name of the pi-atomic ion. That's it. That's the name.
SO4 3.
So aluminum is +3. So you need, and then the SO4 is 2 minus. Whenever you have a +3 and a 2 minus or vice versa, you know that the common denominator is going to be 6. So Al, excuse me, if you can mute your microphones,
Oops.
it's okay. Okay, so if you have a +3 and a -2, you know that the common denominator is going to be 6. So it would be Al2, and then here's the way you would write SO4. So it would be SO4, not a dollar sign, SO4 3. It would be parentheses, and also these would be subscripts. These will all be subscripts. Like that. Oh. Okay, you get the point. This would be an Al. There we go. So that would be the answer, and that would be aluminum sulfate. And you can see how, so SO4, whenever you have multiple of a polyatomic ion, you need parentheses, because if you don't have parentheses, it would look like SO43. That's really the only reason why. Okay, next one. Chromium, which is chromium 2, where they're telling you the charge of it, so chromium 2 plus, and hydrogen carbonate. So hydrogen carbonate, as opposed to just carbonate is CO3 2 minus, and hydrogen carbonate is HCO3 minus. So they're very similar. So chromium, hydrogen carbonate, HCO3 minus. So if that's the case, all you need is Cr. You need 1 chromium, and you need 2 of the hydrogen carbonates. Like that, because each one of them has a +1 charge. You need 2 of them to cancel out with the positively charged, the +2 charge chromium. Like that. Okay, so is there any questions on that? No? Okay. Cool. So now let's write the formula. These are very easy. Let's write the formulas for some covalents now. So dinitrogen, or you could just say it in the chat. I'll keep the chat window up. So dinitrogen tetroxide. What is that? Just the formula of it. Good. NO2, or N2O4. Now prefixes. Oh, these slides suck. I don't like these slides at all. So prefixes, I'm gonna write them down here. So you have mono, di, tri, tetra, penta, and then hexa, and then it just keeps going. So by the shapes. So this is where this is the prefixes for covalence, and the only one that's kind of difficult is tetra. You don't really think, you think of like quad or quattro or something, quadro, or I don't know. You think of something different when you think of, you don't really think of tetra, but tetra means 4, like Tetris, for example. So mono, di, tri, penta, hexa, and then after that it's just hepta, nona, or hepta, octa, nona, deca, whatever. It goes by the shapes. So mono, di, tri, and tetra are the really important ones for the prefixes that you should have memorized. The other ones, it's easy to, if you know basic geometry, it's easy to understand. Okay, so we're writing the formulas. We did that one. What about the next one? Sulfur hexafluoride. Anybody in the chat? Just one person, or whoever does it first. Sulfur hexafluoride. Good, SF6. Awesome. Good job, Sarah. All right, next, diarsenic trisulfide. This might be tricky. Good, As2S3. Good. I was afraid someone was going to put AR, because, oh, arsenic is AR. No, so argon is AR, arsenic is AS. So good job. Okay, good. The answer is nice. All right, so we're going to talk about acids a little bit, not too much. There may be one question on this on the exam. So an acid, so right that we were talking about ionic and covalent. An acid is a little bit different. This is when I was mentioning before how when you have hydrogen, when it's in an acid, likes to ionize and become hydrogen +1. This is when the periodic table trend takes into effect, when you have hydrogen as a positive charge. Most of the time, hydrogen is involved in covalent bonds where it does not have a positive charge, and it is sharing electrons with other nonmetals. So acids have an H and then something else. That's basically what happens. And here are some examples of acids. Let's keep going. So HCl, hydrochloric acid. HBr, hydrobromic acid. And you can kind of see how they're named, right? Hydro, hydrogen. Chloric, is chloride, it becomes ic for some reason. That's exactly the rule. And same thing and then there's an acid at the end. Now, the acids, when they are ionized in water, when they're added to water, they actually break down. And they break down into their hydrogen plus component and whatever is left over, their anionic component. In hydrochloric acid's case, it will be hydrogen plus, Cl minus. Hydrobromic acid, hydrogen plus, Br minus. So for naming these, it's not too hard. Here's this little schematic that tells you exactly how to name them. This is very easy. So if the anion does not contain oxygen, for example, hydrochloric acid, hydrobromic acid. If it doesn't, you add hydro in the beginning. The anionic root, meaning chlorate, chloride, whatever the anion is, the root word of it, for oxygen it would be ox. It wouldn't be in this case because it wouldn't contain oxygen. Anyway, but for chlorine it would be chloride. For iodine it would be IO, IDO, IDO, or not IO. Yeah, it would be iodide, hydroiodic acid. And then you add an IC ending. So it's hydro, anion root, ic, acid. So that's a little schematic there. If the anion does contain hydrogen, meaning if the anion oxygen, I'm sorry. If the anion contains oxygen, such as carbonate, sulfate, phosphate, a lot of these polyatomic ions have oxygen in them. A lot of them do. Actually, most of them do. Then you need to check the ending of the anion. In this case, they're polyatomic. All of these are polyatomic. So you have things like sulfite, nitrite, chlorite, perchlorite, or hypochlorite. If you have that, an IT ending, you get rid of that ITE ending. The IT turns into an US, OUS, and turns into the root, meaning if it's sulfite, it would be sulfurous. So it's kind of weird, but it'd be sulfurous acid. If it was nitrite, it would be nitrous acid. Then if you have polyatomic ions containing oxygen, such as that have an ATE ending, such as carbonate, sulfate, phosphate, nitrate, you will do the same thing, get rid of the ATE ending, and put an IC ending. So it would be sulfuric, nitric, chloric, perchloric acid. And you can have a bunch of those names. So this schematic, we're going to copy it into our next two examples. So here's examples. So here's what acids are going to look like. In another disclaimer, they're all going to have a hydrogen in front and then some kind of anion component. So they're going to have nitrate, nitrite, sulfate, sulfite, phosphate here. This is acetate. So you can see how the nitrate becomes nitric acid. The nitrite, ITE, look at the schematic, ITE, where are we at? So ITE becomes us, OUS. So the nitrite becomes nitrous. Sulfite becomes sulfurous. And it's not sulfus, it's sulfurous. Why? Because it sounds better, it rolls off the tongue better. No other reason, honestly. So yeah. And phosphate, you have phosphoric. It's not phosphic, it's just phosphoric. It sounds better. Acetate would be acetic acid, and that follows the rule pretty well. Okay, so here are some other ones here's all the chlorate. So all the chlorite, chlorate, hypochlorite, perchlorate, all these different chlorites, these chlorine and oxygen containing polyatomic ions, when in their acid form, here are their names. So if they follow the rules pretty well. So hypochlorite, okay, you take hypochlor, get rid of the ITE, add an OUS, hypochlorous acid. Chlorite, ITE, get rid of, add an OUS, acid. Chlorate, get rid of the ATE, put IC, chloric, acid. Perchlorate, get rid of the ATE, add an IC, perchloric acid. Okay, so is there any questions on that? So for an exam, I would expect you to name the simple acids. If I gave you HCl and I gave you HClO, right? I would expect you to know the difference between those. So one of them is hydrochloric acid. The other one is hypochlorous acid. So that could be difficult, but knowing the rules of, if I see an OUS, like if you try to deduce the information going backwards, if I see OUS, that means it was definitely a polyatomic ion containing oxygen, and it was probably one that contained a low number of oxygens, either one or two. So it would be chlorous. So chlorus would be hypochlorous would be deduced from hypochlorite, like this. So hopefully that makes sense.
I have a question.
Yeah, what's up?
How did you know how many hydrogens to put in? Because if you go into the other slide before,
Yes.
they're not all just one
some of them are what we call polyprotonated. So good question. And the way you know is by the charge of that polyatomic ion. So NO3, if you look at the charges of them, where are they? You look at these. So if you have nitrate, NO3, it's -1. So that means its acid is going to be HNO3 because it's a +1 for the hydrogen, -1 for the anion. And so it's based on just the charges. Sulfate and sulfite are going to be H2SO4 and H2SO3 respectively. There are other ones such as phosphate's not here. I don't know why phosphate's not here. It's important. Phosphate is, I'll just write it here for a second. Phosphate is PO4 -3. So if this was in an acid, phosphoric acid, you would have H3 because you need 3 positively charged hydrogens to cancel out the PO4 in essence, because when they ionize, and it would be H3PO4. So it's based on purely the charge of the anion is what tells you how many hydrogens. Good question. Okay, moving on. So let's name
sorry.
Oh no,
sorry.
it's okay.
For the exam, we're not just gonna have to memorize, the names and their corresponding abbreviations, but you're also gonna have to know the charges.
Correct. So
Okay.
the names charges and formulas. Yeah, so I'm sorry. Names, charges, formulas for all the polyatomic ions, for the common ones. So
Okay.
that's an integral part of chemistry. That's why people don't like chemistry. No one said it was fun, but I'm trying to make it fun. Okay, so good. All right, let's name these acids. Oh, if we look at our chart, it's still there we go. Look at our chart. Let's look at it. Does the anion contain oxygen? In this first case, it does not. All right. Hydro, anion root. So it would be hydro. The anion root is sulfide. So and it would be to get rid of the IDE and add ic. So it would be sulfuric acid. So it would be hydrosulfuric acid, different than sulfuric acid. That could be a pain, and I understand the difficulty there. So sulfuric acid is H2SO4. Hydrosulfuric acid is H2S. So yeah, that's kind of weird. Okay. Next, HClO3. Does the anion contain oxygen? Yes. Check the ending of the anion. So ClO3 is chlorate. Not perchlorate, but just chlorate. So this was on the previous slide. It would be, it's an ATE. So we have, what am I doing? So you have, you have chloric acid. That's it. Yeah, it's very easy. You just have chloric acid, short name. Next one, so I'll write down chloric acid. Chloric acid. Then HNO2. So NO2 is nitrite with an ITE ending. So we look, does it contain oxygen? Yes. What is it? Nitrite. You make it nitrous acid because you get rid of the ITE ending, add OUS, and then acid. So nitrous acid, like that. Okay, cool. We got it, and we have a chat. Hydrochloric. What about hydrochloric? For this, no, it would just be chloric acid. So hydrochloric acid is, if you look at the rules, so you only add hydro when there is a anion that doesn't contain oxygen. So if it was just HCl, that's hydrochloric acid. So just like I was mentioning that hydrosulfuric acid and sulfuric acid are different, chloric acid and hydrochloric acid are different. So hydrochloric acid equals HCl. Whereas chloric acid, you have chlorate and you change it to IC, make it chloric. So chlorate is ClO3. Yep, this stuff kind of sucks, I know.
So why does the presence of an oxygen in the element or whatever eliminate the hydro?
So it's a good question. I don't really know. That's just they came up with that. That's just the way they name it. I don't think there's no real scientific reasoning for that. So nomenclature wise, if you didn't have a hydro, and it would be, they just need to make a distinction between the two. That's kind of it. Because as you can see, like sulfuric and hydrosulfuric are clearly different. So if they didn't have that distinction between the hydro and the not hydro, you would have a problem in naming. So either one, like they had a choice. They could make hydro on these ones, or they could have had hydro on the other ones. But they chose hydro to be on the ones that do not have oxygen contained in the anion. So it's kind of just the naming preference that they discovered, that they chose. That's a good question, though. Okay, let's do some other ones, but let's go backwards because more practice is better. Okay, so we're going to do chlorous acid. All right, let's break down the name. Chlorous acid. So it's got an OUS, right? So let's look at the chart again. Kind of bring it up. Here we go. So chlorous has if you go from OUS, that means its root has an ITE ending. So that's chlorite. chlorite. Calcium chlorite, and it's an acid. The acid should tell you, oh, it has a hydrogen in front of it. So that's the case. All I need is a chlorite with a hydrogen. Hydrogen in front. Chlorite is ClO2. Hypochlorite is ClO. Oh, no, wait. Yeah, it's ClO. Okay, that's correct. So hypochlorite is ClO. All right, does that one make sense? Before we go to the next two, I know this is probably where a lot of questions come up. Is there any other questions about why this is? No? All right, then we are good. All right, next, phosphoric acid, IC. It's got an IC ending. So that means if you go backwards, IC ending usually ends in AT, or definitely ends in ATE. So phosphate. Then we have acid, which means is a hydrogen. But since we know that phosphate, PO4, is a -3 charge, then it's not just one hydrogen, it is multiple hydrogens, H3PO4. So the reason why I kind of overlooked that in the first example is because chlorite is a -1 charge, so it just needs one hydrogen. But in phosphate, it's -3, so it needs 3 hydrogens. Next one, hydrobromic. All right, this one we kind of went over before, but bromic, hydro, whenever you see hydro, think, okay, it's either a singular, if you ever see hydro, it's usually a singular anion. It's not polyatomic. Because all the polyatomics, most of them have oxygen in them. So hydrobromic, HBr, that's it. Wherever you see hydro, it's probably a singular atom. Hopefully that helps. Okay, any questions on those? No? Okay. All right, so there's some good things to think about. How do you know whether a compound is ionic or covalent? Anybody want to answer me that? Like, what's the easy way to figure out how to figure out which one's which? Either
One way is to look at what's being bonded.
Exactly, what's being bonded. So if you have, just like good Sarah, good Brandon. So if you have a metal involved, metal and a non-metal, it's going to be ionic. If you have more than one non-metal, it's going to be covalent. So that's very simple. Think about this. What kind of do you expect? That's stupid. I don't like that. Who cares? Don't think about that. All right. Who likes Fairly Odd Parents, right? I made this slide a couple years ago to my other classes, and they like it. It's a good summary of all the rules. So you see how ionic between metal and non-metal. Metal loses electron. Non-metal gains electron. The metal cation total charge should be equal and opposite of the non-metal anion charge. Charges you should know. Here's the ones. Transition metals have variable charges. Naming with transition metals uses Roman numeral for their charge. Polyatomic ions, IDE ending, except for polyatomic ions. Covalent, between two nonmetals, no charges. It's not dictated by charges, but there are charges involved, which we'll talk about when we talk about intermolecular forces. But for the first element of covalence, you write the name of it. If there are more than one, you write the prefix. So such as N2, some N2O would be dinitrogen monoxide. The second element, you write the name of it with the IDE ending, and you always use a prefix. So use a prefix regardless of how many there are. So yeah, this is a really good slide. This is slide number 30. So you can put that, the rules. Okay, moving on. So now we're gonna get into some math. Or is there any questions about any of this before we move on? Because we're kind of moving on to an adjacent topic, but it was getting into math a little bit. It's not gonna be identical. Okay, moving on. So empirical and molecular formulas. So let's just go over some definitions. There's a thing called empirical formula. What that means is the simplest ratio or the most simplified version of a compound. The molecular formula is the actual number of atoms in the compound. So the molecular formula is just whatever the molecule is, that's what it is. The structural formula it shows line diagrams of how, if I had my pen working right now. Okay, next week we'll do that. Let me try it one more time. The cursor works fine. Then when I write, it goes over there. It should be, okay. Maybe my pen is, I think I dropped my pen during the move. So, I don't know, maybe it was cheap. Whatever, we'll figure that out. All right, so then
What
a
if you
structural,
write with the cursor instead of the pen?
I think we'll do this thing. Let me see. I think you need the pen. Hold on. I have a touch screen, so that didn't work. Yeah, it detects the pen. And so right now, anyway, I'll figure it out. I don't want to waste your guys' time. Okay. So thank you for the tip though. But I think I'll figure it out. I'm sure it's not broken. Maybe I just have to like recalibrate. There's an app program to recalibrate it. I'm sure I have to do that. Okay. So the structural formula describes the 3D arrangement of the atoms in the compound. So there is stick models that you can draw for this compound, which is butane, and for really anything. But today we're going to be more focused on empirical and molecular formulas. So the empirical formula for C4H10. C4H10 is butane. It's a gas and organic. It could be it's flammable organic gas. And this is the molecular formula for it. It's the actual number of atoms in the molecule, right? So the empirical formula for it would be C2H5. That is the most simplified ratio of atoms in the compound. So that's what we mean by empirical formula. It doesn't really have an importance when we're talking about the molecule, but when we're talking about mathematically and trying to figure out some kind of problems, it does have a significance. But for now, just know that it is the simplified formula. And we're going to figure out how to determine the empirical formula. We determine by elemental analysis, blah, 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 which we're going to do right now. So finding the empirical formula. Now I'm going to go through this and then we're going to do a couple of the example problems. Okay, so the kind of questions you're going to get. Oh no. So the kind of questions you're going to get. All right, so here are the kind of questions you're going to get for empirical formula. Let's say you have 100 grams of a substance. It contains 38 whatever grams of carbon, 16 grams of hydrogen, 45 grams of nitrogen. What is the empirical formula? Now there's a way to figure this out, and we're going to go through stepwise. Another way that they can word this question is you have a substance that contains 38% carbon, 16% hydrogen, 45% nitrogen. What is the empirical formula? Those are basically the same questions because the first step is to convert percentages to grams. If you're given a compound with certain percentages of their starting material or their atoms, you can convert that to 100 grams. Just say the total sample is 100 grams. And those percentages could be directly converted from percent to just gram. No conversion factor, just make percent gram. Then you convert grams to moles, just like we talked about last class. So you now have the grams, 38 whatever grams of carbon, you divide that by 12. The hydrogen you divide by 1, the nitrogen you divide by 14, which are the molar masses, the average atomic masses of carbon, hydrogen, and nitrogen respectively. That will give you the moles. Then you divide all of them, all of those mole numbers, by the smallest number of moles. And the reason why is because this is a form of reducing them to a kind of whole number, reducing them to whole numbers or whole number multiples. To do this, you just divide. Then you multiply all the mole ratios by an integer to make them whole numbers. Okay, so is there any questions on what any of that means before we actually see an example? And you'll see what I mean. If 3 and 4 are a little iffy right now, you'll see what I mean. Okay, let's get started. So the first thing we're going to do is we are going to convert, if I have my pen right now, but I don't, but it doesn't work. Ugh, I would love to do this by hand, but I'll talk you through the work. If you have 38.67 grams of carbon, we want to convert that into moles. To do that, we divide it by 12.011, which is on the periodic table, the average atomic mass. So you get something like 3 point something. Then for 16.22 grams of hydrogen, you divide it by 1.008 grams per mole of hydrogen. You get around 16. For nitrogen, you divide 45.11 by 14, which is the molar mass of nitrogen, and you get 3 point something. So they did that. For carbon, they got 3.33. For hydrogen, they got 16, around 16. For nitrogen, they got a 3.219. Next is you are going to take the lowest number of those. Out of all the moles, the lowest number. All right, 3.219. That is the lowest number. And you are going to divide it. And I'll do that on my calculator along with you. You are going to divide all of these mole numbers by the lowest one. So if I divide 3.33, which is the moles of carbon, by the lowest one, 3.219, I get 1.03. For our intensive purposes, that's about 1. Sometimes, because we are approximating when it comes to molar mass, we're approximating, we're rounding. There's some level of rounding in these molar mass numbers. It's actually 12.011, blah, blah, blah. There's more to it. So that some sense of rounding will make our numbers, our whole numbers, not exactly whole numbers. You might get 1.01, 0.99. But if it's very, very close, you can say, all right, it's 1. Or if you get 0.499, all right, it's 0.5. And you'll see why in a minute. So for carbon, once you divide it, you get 1.03, approximately 1. That means you can say the ratio for carbon, and look, I'm looking down here now, ratio of moles of atoms, you know that carbon is 1. And it is just saying the ratio based on the moles, the molar ratio, and once you divide it, you get 1. Hydrogen, 16.09. So let's do that. 16.09 divided by the lowest number of moles, 3.219. I get 4.998. For all essence, that is approximately 5. So you put 5 for hydrogen. For nitrogen, you're dividing 3.219 by itself. So you get 1. And you get a ratio of 1 to 5 to 1. That is the empirical formula for whatever this compound is of CH and N. So it'd be CH5N. Okay. Is there any questions on how to do the empirical formula from that method? Okay, so there's one thing I have to add. Sometimes when you do that, the last step, the division by the lowest number of moles, you might not get a whole number. You might not get 4.99, 1.001, whatever. You might get 1.5. You might have 1, 2, and 1.5. If that's the case, multiply everything by 2. If you multiply everything by 2, let's say you have 1, 2, and 1.5, you will get 2, 4, and 3. That will be your empirical formula now. Same thing works with if you have exactly 0.33 or exactly 0.25. For 0.33, you'll multiply the entire ratio by 3. For 0.25, you'll multiply the entire ratio by 4. So hopefully that makes sense. All right, so there's another example, I think, yes. All right, so there's a laboratory analysis and you have aspirin. Aspirin, 100 grams of aspirin, or here's the percentages of carbon, hydrogen, and oxygen in aspirin. So you take these percentages, convert them to grams. So you basically say 100 grams of aspirin will have 60 grams of carbon, 4.47 grams of hydrogen, 35.53 grams of oxygen. Then you are going to use the molar masses of carbon, hydrogen, and oxygen and divide to figure out the moles of each of those elements. So you do 60 divided by 12.01, 4.48 divided by 1.008, 35.53 divided by 16. So before we show the work, the rest of it, I'll just do it by hand, and you can do it along with me or stop me. For the first one, for carbon, the 60 divided by 12, I got 4.99, so that's 5. For the hydrogen, I assume I get 0.008. I get 4.44. And then for the oxygen, 35.53 divided by 16, I get 2.2. So our lowest number is 2.2. So let's see where they go from here. All right, so they did the moles, they did all the moles. So they have 4.99 of carbon, 4.44 of hydrogen, 2.22 of oxygen. Now we want to divide all of the numbers, all of those mole numbers, by the lowest amount, by 2.22. So if we divide the carbon by 2.22, 4.996 divided by 2.22, I get 2.25. This is what I was talking about before. It's not a whole number. I get 2.25. If I divide 4.44 divided by 2.22, I get exactly 2. So that's good. That's a whole number. So right now I have for carbon 2.5, for hydrogen 2, and then for oxygen, since we are dividing by itself, 2. There's our ratio, divide by the smallest whole number, you get this. You get carbon 2.25, hydrogen 2, oxygen 1. Now what the hell do you do? So just like I mentioned before, if you have a weird 2.25 or 2.33, something like that, you multiply the entire ratio by a whole number that will get all of these numbers, these subscripts as whole numbers. And that would be 4 for this case. If you multiply 2.25 by 4, you get 10. Multiply 2 by 4, you get 8. And multiplying oxygen by, or 1 by 4, you get 4, sorry. So you get, oh wait, what did I say, 10? I meant 9. You get 9, yeah. I'll move this up. Yeah, okay, cool. So you get C9H8O4, which is the empirical formula, which is the formula for aspirin. Sometimes empirical and molecular formula can be the same, such as carbon dioxide. Carbon dioxide is CO2, and the empirical formula is CO2, because you can't reduce it anymore. Same for aspirin and a lot of other compounds that you can't, that don't have all even numbers in their compounds that you can't reduce. So, yeah, okay. Is there any questions on that, on those two examples? That encompasses pretty well how to do empirical formula, I think, but please ask questions. No? Okay, moving forward. All right, we get it. Here we go. This is different now. So oh, there's a chat question. I'm sorry. Let me see. So Daniela said, is the molecular formula where you multiply? Yes. So Daniela, that's exactly what we're going to get to now. Is from the empirical formula, how do we get a molecular formula? Sometimes the question might ask you, what is the molecular formula? And it might give you some additional information. So if we know that the empirical formula is a very simplified version of the molecular formula. What that means is it's a subset. It's a division of it. So in other words, if you multiply the empirical formula by a number, you get the molecular formula for whatever molecule you're talking about. So here's how you figure that out, and we'll do an example. Okay. So if you're given, or let's say you figure out the empirical formula for a compound containing carbon, hydrogen, and oxygen has a mass of 86.03. You calculate the atomic mass by doing, oh, sorry, wait. No, that's not true. So you have empirical formula of C2H3O. That's you do an empirical formula question to figure that out. So we kind of skipped a step. Let's say you did all the empirical formula of math. You figured out C2H3O. The question saying, oh wait, but the compound itself has a molecular formula that has a molar mass of 86.03. How would you go about figuring out what the molecular formula is? Basically, what you do is you first, I don't even like to look at equations. What I do is, basically, you're first trying to figure out the molar mass of the empirical formula, and you're trying to figure out how many times that goes into the molecular or the molar mass. So how many times the empirical formula goes into the molecular formula, then multiply it by that number. That's basically what we're doing. So if you do that math, the empirical formula is 12 times 2, which is 24, plus 3, which is 27, plus 16, which is 43. So you get 43.04, whatever. We're trying to see how many times that goes into the molecular formula of 86. When you divide those two numbers, you get exactly 2. When you're done, you take 2 times the empirical formula, and you get C4H6O2. And that is the molecular formula for this specific problem. Okay, is there any questions on that? Any questions? No questions? Okay. All right, combustion. Okay, combustion's good too. So combustion, kind of different. It's kind of different, but in combustion equations is when I give you a lot of examples with empirical formula. So let's learn what a combustion equation is first, or a reaction is when you combust something. But it has oh, it's fire. Yeah, it's fire. But there is specific rules to this equation, such as the first rule is that combustion really entails the combustion of organic compounds. So you're dealing with methane, propane, butane, things like that are organic gases usually. Then you add oxygen to them. All the time it's O2. Then you add then they react to produce all the time CO2 and H2O to some extent, and heat. So it would be CO2, H2O. So this is a very defined equation. Combustion is some organic compound. It could be methane, which is shown right here, or it could be butane, propane, or other things that involve CH, or even oxygen, CHNO. And then you add oxygen, and it reacts to produce CO2 and H2O all the time. And these numbers here, these coefficients, are the balanced chemical formula. And we're going to learn balancing, I believe, next chapter after the exam. So the idea is, if you can measure the grams of water and CO2, you can determine the grams of C and H in the compound, and therefore determine what the compound is. So you can use these combustion equations to figure out how much you started out with, and how much, and exactly what did you combust, because you can figure out the ratios. So you can figure out the empirical formula, kind of like I mentioned, but let's just do an example. Okay, so let's do this example. So you have cumin. It's some organic compound. It contains hydrogen and carbon, right? It combusts. You have 47.6 milligrams of cumin, produces some CO2. They don't tell you how much, and 42.8 milligrams of water. Okay, what is the empirical formula and molecular formula? And it tells you the molar mass of the compound is 120. So what we know is that you have 47, you always write down what you know. And this is a bigger problem, so you always write down what you know. Is you have 47.6 grams of this cumin, and it gives 42.8 milligrams of water. We know the molar masses, and we know the molar ratios. So what you can do is figure out what you know first. It gives you always when it gives you a defined amount, figure out the moles and break it down by percentages, such as the water is, wait, I think this is math wrong. All right, I'll figure it out, but we'll go through it. So the mass, the water, you have 42.8 milligrams. So let's look at hydrogen. So hydrogen, there's 2 hydrogens in every water molecule, right? So you're looking for, they did it weird. The math is weird here, but in essence, we can use that number in a minute. So if you figure out the molar mass of water and then divide. So even though it's in milligrams, so you could just, here you can say, I know it's in milligrams, that's just to make it more complicated. You can just put it in grams. That's what I do. Oh, okay. So you can just put it in grams. Let's just say it's in grams. So you have 42.8 grams of water. We're going to divide that by 18.02, which is the molar mass of water. And then we're going to multiply it by 2. That gives us the moles of water. Wait, hold on. It does. It gives you the moles. Why is this written weird? That gives you the mole. That gives you the. Doesn't give you the mass of water. I didn't write this. Mass percent. The mass percent. Okay, so
I think they're doing it all in one big
they're doing it in one
calculation.
step. Yeah, but I don't like that at all. So here's what we're gonna do. All right. So let's do this. Okay, so if you have, let's do it. Here we go. All right, so you have 42 grams. Let's just say everything's grams. So you have 42 grams divided by 18. What do we get there? So let's do it one step at a time. Equals. So let's do. I got my calculator. We'll do 42.8 divided by 18.02. You get 2.37 moles, right? That's of water. Then we're going to multiply it by 2. Multiply that by 2, you get 4.75. So times 2, and the reason why I'm multiplying it by 2 is to figure out the moles of water. I'm sorry, of hydrogen. So 4.75. And now we can multiply 4.75 by 1.008, which would give us 4.79. The reason why we're doing that is to figure out, now that we have the moles of hydrogen, we can figure out the mass of hydrogen that is in 42.8 milligrams, or grams in our case, of H2O. So now we have 4.79. Let's change it to grams to make it more simple. Change everything to grams. So yeah, whatever. Okay, we get it. I think we get it. Hopefully, if you have any questions, you can ask them in the middle anytime, but hopefully we get that the moles of hydrogen was determined by figuring out first the moles of water from the sample, then multiplying it by 2. Then that moles was then multiplied by the atomic mass of hydrogen alone, which is about 1, so 1.008, to come up with our grams of hydrogen. Now, we know that based on the definition of our combustion, that on the left side of the equation, the reactants, the only component that has hydrogen in it is the initial thing that's combusted, right? So in our case, it's the cumin. So cumin contains hydrogen and carbon and hydrogen. So we know that out of this cumin, this 47.6 grams of cumin, I say Cuban, like Mark Cuban, but cumin, that 4.79 grams of it is hydrogen. So from that, we can determine a mass percentage of hydrogen, 10 grams, or 10%. I'm gonna stop there. Is there any questions on that process? No? Okay, cool. Then we know that cumin only contains carbon and hydrogen. Sometimes you might have organic compounds that contain carbon, oxygen, and hydrogen. And for those cases, which I think there's some on the homework actually, for those cases, you need to do the same exact procedure, but with CO2. They wouldn't say some CO2. They would tell you exactly how much CO2. Because you would need that information to figure out how much oxygen in grams there are, then subtract that from, or divide that by the total, and then come up with another mass percent. Okay, so then we can figure out directly the mass percent of carbon in CHEM by doing 100% minus the 10% of the hydrogen to figure out 89.9% carbon. That's the hard part. That's done. So is there any questions up until that point? Because after this, it's just empirical formula. No? All right, then I'm going to continue. Okay, so then we take the empirical formula of this sample by using the mass percentages, turning them into grams. So we take the 89.9% of carbon, turning it into grams, and then we figure out how many moles that is by dividing by the molar mass, 7.49 moles. Same thing for hydrogen, 10.1 divided by 1.008, and we get 10.02. There is a chat. Oh, what did I just do? I clicked the wrong button. Chat. Is this automatically fixed to what you just wrote on the slides? No, but I can upload this instead. I can upload these slides instead. Because I don't like the way that confused me even. Like, that's with the way they wrote it. Okay, cool, I'll do that. I gotta remind myself to do that. So I'm gonna save it now. All right, it'll save it eventually. Oh no. Let me, oh, it's gonna say not respond. Okay, good. If it just crashed on me, that'd be terrible. Okay, so now we do the empirical formula with the hydrogen, and you get 10 moles. Then we're gonna divide by the least number of moles, which is 7.49. Dividing 7.49 by itself, you get 1. Dividing 10.02 by 7.49, you get 1.34, which is about 1.33. You can say that that's about a third, the 0.34. You multiply, it's close enough. Then you multiply the entire ratio by 3, and you get a 3-to-4 ratio. That is the empirical formula. Is there any questions there? No questions? Okay. Then if you go back to the original question, you are given that the molar mass of the molecular formula is a question. How did they convert it to grams from percentages? So you just get rid of the percent sign and put grams. That's literally it. So percent, what is percent? Percent is out of 100%, right? So you can just say, let's just assume our sample is 100 grams. And you can do that every single time. You could assume it's 100 milligrams. You could assume it's 1,000 grams. But the idea is we're just assuming it's a certain amount. But it's a fair assumption. It's not really an assumption. It's a definitive thing. So why not use the original mass of the CHEM given? Because we don't know the mass. We need to know the mass percents. Well, we are using the mass of CHEM to figure out the mass percents of its components, which are hydrogen and carbon, but we don't know the percent components of the components until we do that math. So that's why we do use the original mass. We're using it to determine the mass percents. More specifically, we only use it for hydrogen, but we use it for carbon also by deduction. So hopefully that answers your question. That's a good question. Okay, next, we know that the empirical formula is C3H4, and we can figure out the molar mass of that by doing 12 times 3 plus 4 times 1, 40.01. And you get, sorry, someone's coming over to watch my cat, and I told them, they said they're coming, and I said, cool. All right, so the molecular mass given in the question is 120 grams, right? You're gonna do 120 grams, see how many times the empirical formula goes into 120 grams, and you turn out to the 120 divided by 40, you get 3. So you're basically multiplying the empirical formula by 3, and you get C9H12. And that's the formula for cumin. Okay, so I know that was a lot, that question. Is there any questions on the question, on the problem? So I think the tough part would be getting through this math, which basically just says the logic of it is you're taking what you know. So it tells you 42.8 milligrams of water. You're finding out from that how much water there is, how much hydrogen there is. Because water in the combustion reaction, and only in the combustion reaction, is the only source of hydrogen in the product side. Is the only source of hydrogen in the product side. That means once you figure out that amount, you can figure out how much cumin there was, or how much, what the percent of hydrogen was in cumin. The same thing can be done for carbon, because for CO2, it's the only, for carbon, in CO2, carbon is the, what am I saying? The only source of carbon in combustion products is CO2. So we can also figure out how much percent carbon there is. And by deduction, let's say there was oxygen in cumin, we can say that based on the remainder of the mass, how much oxygen there was left over. And we can figure out the mass percent of that. I hate explaining this, but hopefully that made sense. And then from there, we want to figure out the moles, figure out how much the mass, and then from the mass, we divide by the total amount that is starting with, that we combusted, to figure out the mass percents. Once you have the mass percents, it's simply just doing the empirical formula like we just did, and then the dividing it into the molecular formula. Okay, so I'm actually going to go now, and there's only 8, how many slides left? About 10, 13 slides left, and your TA will take you through the rest. But before I leave, is there any questions? Any burning questions? I'll take a couple minutes to answer them. Oh, Daniela asked me something. Can you tell us how you want to set up the day of the exam before you go? Will it be posted? Oh, that is a very good, very, very good. Thank you, I forgot to mention that. Okay, so the way the test is going to work is that there is going to be, just like we have a normal Zoom, and I will post the exam on a Moodle document for the I can't tell, I'm gonna be exhausted. Hold on, let me get the thing up. Where's Moodle? Moodle. Where's Moodle? Moodle NJIT. All right, and I'll post the exam for only the 3-hour period. So, let's see, new share. I'm going to share my screen. Okay, so hopefully you can see my screen now. You see the schedule on Moodle. So June 1st, exam 1. Here's exam 1 study materials. There's stuff in there you can look over later. There's like hints and stuff, which the hints I'm going to cover in my little review video that I'm making. Also, there's old exams. Yes. So definitely study from the old exams. So here's 2018 exam 1 and the answers, 2016 exam 1 and the answers. They're not exactly the same. Obviously, they're completely different, but the topics are the same. I will post the exam here as a file, as a PDF and a Word. Then you will open it when we start class, and then, or probably like, I'll put it up at like 9:05, or whenever I stop talking in the beginning of class, I'll put it up. Then you can open it, and if you have a PDF, make sure you have a PDF editor or just Word to do the test in the computer. So it's not going to be a Moodle assignment that you do in Moodle, because I hate those. Yeah, they grade themselves and it's easier for me, but it's weird for you because sometimes you might want to write your work. There's not enough room. It's weird. But if you have an open Word document where you can just write whatever you want and do work on the side on a loose leaf paper, go ahead and do that. But it'll be there for you. So after that, you can email me, or you can submit, or actually you would email to the TA. I'll give you her email tomorrow or next week. You can submit the file that way. And Sarah said, could you print it out and write on it, then upload as a PDF? Of course you can, definitely. And I'm gonna put a submission under here. There'll be an assignment submission for exam 1 under this Moodle, but you can also email it to me or the TA if for some reason it doesn't work. And yeah, so yeah, Marlon, to answer your question, of course, yes, you can. And then you can just take pictures of it if that's easier. I know some people like to do that. What else? That's it, I think. I had something else to say, but I forgot. Yeah, so hopefully that answers your questions on that. Calculator is allowed. If you have a question during the exam, I will take you into a separate breakout room. You can ask your question, share your screen, whatever you need to do, and I'll answer your question, then I'll bring you into the rest of the students. Your mics should be off and your video should be off. Your mic can turn on, obviously, or you can use the chat window to ask me a question, or not to ask me the question, but to say you have a question. Then I will take you into a separate breakout room and we can answer the question together. And then I'll bring you back into everybody else. And yes, you'll be on the Zoom, you'll be on Zoom when you're taking the exam. So that's to ensure that, to mitigate cheating and stuff like that, so that you'll be in the session when you're taking the exam. Okay, so is there any other questions about the exam or anything else going forward? No? Okay, so if not, I will bring the, I will get the TA on the, hold on, how do I do this? I need participants. So I will make Jiang Shan the host, and you can have,
Okay.
Hello. So,
Hi.
and she's gonna be teaching the rest of it. Do you have the slides up?
Yes, I have the slides.
Okay, good. So one more thing. So Marie asked, how do you get into the breakout room? So when you have the questions, I will assign you to the breakout room, and it would just say on the, and it would pop up, join this breakout room, and you click join, and then and then we can ask the question that way. Okay. So can you can share your screen.
Okay,
Yeah.
let me try.
Yeah, try it before I leave.
Can you
Okay,
see my
great.
screen? Okay.
Good, yes, everybody can see it. And then what you can do is you can end the recording. It should say on the little bar, recording and record, whatever, after the lecture is over. And then do you have the breakout room button on the bottom or somewhere?
Let me see. I think when I close this share,
Yeah, when you close.
I can see it breakout.
Yes.
I can see that. Yes.
Okay, good, good. All right, so I think you got it from here. Is there any other questions from anybody else before I leave for the day? Okay, if not, I'll keep you updated if anything happens with the exam. It won't. I'll keep you updated. I'll send an announcement for when I upload the review video that I'm gonna put on YouTube. All right, so good luck, everybody. It was a good class. I will go now, and have a great weekend, and stay safe, of course. Okay, bye-bye.
Bye. So hello everyone. So let's continue. So next is we will cover the molar mass and the percent composition. The first is the molar mass. The molar mass is the sum of the atomic masses of elements in a compound, and its unit is gram per mole. So you need to know 1 mole of a compound equals to 6.022 times 10 to the 23 molecules, and 1 mole of the atoms equals this amount of molecules. Okay, so make sure you know the units, which is the gram per mole. And then is a question 1. So what's the molar mass of the iron oxide? I don't think I can see the I can see any chat window or something. It's not showing here. Okay, let's continue. So the molar mass of the iron oxide is, you should choose A, which is 159.7 gram. Okay. And the next is a question 2.
Can you go back? How come it's A? How do we do it?
Yes, you need to know what is what is iron oxide should be. Okay, iron oxide should be Fe2O3.
Okay, I got it now. Thank you.
Okay, sure. So, and then it's a question number 2. How many grams of oxygen are present in 1 mole of iron oxide? So from the previous question, we know the molar mass of the iron oxide, right? Which is 159.7. From that one, you will know how many moles of the oxygen in this 1 mole of the iron oxide. And then you can convert the moles to the grams, which you should choose C, should be 48 grams of oxygen. Because iron oxide is Fe2O3, so 1 mole of iron oxide should have 3 more of the oxygen, and 3 times 16, which is 48 oxygen. Okay, that is question number 2. And then it's like a combined questions. How many molecules are in 50 grams of this PbO2? How to do that? So from the 50 grams, you need to find the molecules of this compound. 1 mole equals to 239.2 gram, which is converted from the molar mass. And then 1 mole is also equals to 6.022 times 10 to the 23 molecules. Okay, so it has 2 equation here. So 1 mole equals to 239.2 gram, and also this amount of molecules equals to 1 mole. So when you have 50 gram, you can times all of them together. So 50 grams times this one times this one. So the mole, and this is a gram, and then you will get the molecules of these compounds. Okay. Any questions for this one? Okay, let's continue. The next one is the percent composition, which is the percentage by mass of each element in a compound. As we should know, the sum of the percentages of all elements in a compound should add to 100. The percentage composition can be determined from the first, the formula of the compound. The second one is the experimental mass analysis of the compound. So how to do that from the formula? For example, calculate the percentage composition of the oxygen in hydrogen oxide. So first, we should know the mass of the oxygen atoms, which is 15.99 gram. And then we know what's the molar mass of the hydrogen oxide, which is 18.01 gram. So the percentage composition of oxygen in the hydrogen oxide should be 15.99 divided by 18.01 times 100%, which is 88.8%. Okay, remember this is a percentage by percent composition, which is the percentage by mass. Okay. And then we will learn the mass percent as a conservation factor. The mass percent tells us the mass of a constituent element in 100 grams of the compound, which means in 100 grams of the compound was the mass of one of the atom, like that. For example, the fact that sodium chloride is 60.65% of chloride by mass means that 100 grams of sodium chloride contains 60.65 grams of chloride, which this number can be used as a conservation factor. For example, we know 100 grams of sodium chloride equals to 60.65 grams of chloride in this compound. Okay. And then is a question. Calculate the mass percent of oxygen in sodium hyperoxide chloride. We should choose option C, which is 52.3%. So for this one, you need to calculate first the molar mass of the sodium chloride O4, and then calculate the mass of the oxygen in this compound, which should be 4 oxygen in it, and then divide them and times 100%, and you should get the option C. Okay. Okay, next question is find the mass of table salt containing 2.8 grams of sodium. So for this one, you should know. You already know the 2.8 grams of sodium, and you need to find what's the mass of the sodium chloride. As we just talked about, the mass percentage can be used as a factor, relationship factor. So that, let's see, 58.45 grams of sodium chloride equals to 22.99 grams of sodium. And then that is 39.33% of sodium in the sodium chloride. So the factor is like this one, 100 grams of sodium chloride and 39.33 grams of sodium. And we apply them together. Because we want to find the sodium chloride, the mass of sodium chloride, so we need to put the sodium underneath, okay? So 2.8 grams of sodium times 100 grams of sodium chloride divided 39.33 grams of sodium. And the final answer is 7.2 grams of sodium chloride. Okay, next one. So next question, which of the following will have a greater mass percentage of oxygen? So for this question, you should also think of how many oxygen in the compound, like in hydrogen oxide, 1 oxygen in the H2O. In the hydrogen peroxide, there is 2 oxygen in H2O2. The same for the HOCl and HClO2. Okay, you need to think of both oxygen and also what is the molecular mass of the compound and do the mass and find out which one has a greater mass percentage of the oxygen. And the answer is H2O2 and also HClO2. Any questions? I think this is the last page of the slides. Yes. So let's go over a little bit. So at first, we are talking about the molar mass, which is sum of atomic mass of the elements in your compound. And you need to remember the units is gram per mole, which means 1 mole was a gram of this compound, okay? And then we are talking about the percent composition, which is the percentage by mass of each element in your compound. This is very important because it's not only let you know what's the mass percentage of one element, but also it can be used like a factor, conversation factor, okay? I think pretty much it is. Let's stop the sharing the contents and you can start your homework.